Everything we have built so far detects fraud while it is happening, which is worth precisely nothing if the transaction still goes through. The alert has to become a decision, and the decision has to reach the authorization path before it answers. Inside the same window we opened this series with. That is a different engineering problem from detection. Detection can be clever. Mitigation has to be boring, and it has to be fast, and it has to be right when the same message arrives twice. The instinct is to write the block to the transactions database and let the authorization service check there. Look at what that actually asks for. Every single authorization, fraudulent or not, now does a read against a database under write load inside the tightest budget in the system. We already know how this ends because it is the same disk and the same locks we walked through in episode 1. The check is not occasional. It is on the hot path for every transaction the bank processes. So it is the one lookup that absolutely cannot get slower when things get busy. That is what an in-memory store is for. So the shape looks like this. Flink detects the pattern and writes a block for that card into Redis. That is the only writer. The authorization service, which knows nothing about Flink or patterns or windows, does one lookup against Redis for every transaction and gets back a decision. The write path and the read path are decoupled by a store that answers in memory. And notice the direction of the dependency. Authorization does not call the fraud engine. If the whole detection pipeline fell over right now, authorization keeps working. It just stops learning about new blocks. That is not an accident. It is the point. The fraud engine must never be able to take payments down with it. Here is the part that gets skipped and then hurts. That block is going to be written more than once. 2 patterns can fire on the same card. A stream gets replayed after a failure, which is exactly what episode 7 is about. So the action has to be idempotent, meaning applying it twice is the same as applying it once. Setting a key to blocked is naturally idempotent. Incrementing a counter is not, and neither is sending a customer an SMS, which is how someone gets 9 identical fraud texts at 2 in the morning. So write the state idempotently, key the side effects by something stable, and give the block an expiry, because a block with no expiry is a permanent decision made by an automated rule at 2 a.m., and a real person has to phone in to undo it. Last thing, and it is the one that makes this design honest. The lookup is not the only cost. There is the network hop to Redis, the deserialization, and whatever the authorization service does around it. And that all has to fit in the window alongside the actual payment work. So you measure it, and you measure the tail, not the average. Because the average is a comfortable lie. The transactions that time out are living in your 99th percentile, not your mean. And you decide now what happens when the lookup fails or is slow. Fail open and approve, or fail closed and decline. That is a business decision about the cost of fraud versus the cost of declining a real customer. And it is better made deliberately in a meeting than accidentally by a timeout at midnight. The loop is closed. Detect, decide, act inside the budget. Which raises the question I have been deferring for 3 episodes. What happens when a consumer dies halfway through this with state in memory and events in flight? Next episode. Exactly once, checkpointing and back pressure. See you there.